everyone, and welcome to the lecture on enols and enolates in the third edition of Klein. This is chapter 21. Okay, so we're going to start talking about what an enol and enolate is. But before we can do that, we need to go over some definitions. So I want you to call your attention to the carbons in this ketone. The carbons that are directly attached to the carbonyl carbon are called the alpha carbons. The carbons directly attached to those are the beta carbons, and then the gamma carbons, and then the delta carbons. So the reactive carbon that forms an enol or an enolate are the alpha carbons, and so those are the ones we're going to spend the most time talking about. So I want you to recall that I said that there were two alpha carbons on the ketone in the previous slide. And so oftentimes there will be two alpha carbons, particularly with a ketone, but they won't necessarily have hydrogens, right? For example, if we take a look at this ketone, the alpha carbon on the right has two hydrogens, but the alpha carbon on the left does not have any hydrogens. You cannot form an enol or an enolate from an alpha carbon without any protons attached to it. And the reason will be evident when we start looking at the mechanism to form an enol or an enolate. Here's another ketone. In this case, it's cyclic. Again, there's two alpha carbons with ketones. This position has two hydrogens, so it's reactive to form an enol or enolate. The other alpha carbon does not have any hydrogens attached. The position is blocked with methyl groups. So this would be a non-reactive alpha carbon for this chapter. Let's look at an aldehyde as an example. Aldehydes have that characteristic carbon-hydrogen bond between the carbonyl carbon and a hydrogen directly attached. So they only have one alpha carbon. And as long as we have at least one hydrogen in this position, there are actually two, but only one is drawn in, then we will be able to form an enol or an enolate from this substrate. Let's look at the difference in structure between an enol and an enolate. Notice that the enol has an alcohol directly attached to a carbon-carbon double bond, or an alkene. The name is derived from alkene -ol. And we form it from a ketone or an aldehyde that along with the alpha position that has at least one hydrogen attached, using catalytic acid or base. If we treat a ketone or an aldehyde with an alpha hydrogen that has at least one hydrogen, with a strong base, instead we will form what is known as an enolate. Enolates have a full negative charge that is shared between the oxygen and the alpha carbon. Either way, the alpha carbon has now become a nucleophile, and it can react with a variety of electrophiles that we'll see in this chapter. For example, a halogen, and for example, introducing this alpha halogenated ketone type structure for the product. So if you just have a ketone, even just a sample of the pure ketone, if there's even a catalytic amount or acid or base around, it will exist in equilibrium with its enol. And again, recall that an equilibrium, right, is a distinct conversion of one structure to another. In this case, these are related as constitutional isomers, the ketone and the enol. And just a catalytic acid or base will convert the keto form to the enol form. These two structures are called tautomers. The definition of a tautomer is rapidly interconverting constitutional isomers that differ from each other in the placement of a proton in the position of a double bond. So recall what constitutional isomers are. Those are structures that have the same molecular formula but have a different atom connectivity. So notice that the hydrogen from this alpha position has been transferred to the oxygen, and the placement of the double bond has also moved from between the carbonyl or carbon oxygen bond to between the carbonyl carbon and the alpha carbon. You can see tautomers, right, exist even in cyclic structures, with the equilibrium heavily favoring the keto form. Typically, it is more stable because carbon-oxygen double bonds are very stable. So those will dominate the equilibrium and will have a majority of the keto form in solution. There are some exceptions to the keto form being the dominant form at equilibrium. Specifically, here's one exception. When we have a 1,3 diketone, then the keto form is actually the minor form, the minor tautomer, right, at equilibrium. And that's because in this case, the enol form is particularly stable. It's stable due to intramolecular hydrogen bonding, and also the fact that this pi bond is now in conjugation with this carbonyl. So the series of overlapping 4p orbital system here is very stable, and it actually additionally extends up to this oxygen. Or one of these lone pairs is also in a p orbital, so it's really a 5-atom conjugated system, and that's a very stable situation compared to 2 isolated pi bonds. Here's another example where the enol actually dominates the equilibrium, and it is the case of phenol. Phenol, as you might note, is typically drawn this way, and there's a reason for that. It's because 99.99% of the molecules will exist in the enol form, not the keto form. There's a few reasons for that. Once we have a pi bond here, right, the major reason is now we have an aromatic ring. If you look over here, this carbon has 2 hydrogens attached to it, and therefore it does not have a p orbital, and this constitutional isomer is non-aromatic. So in addition to being aromatic, it's also resonance stabilized when you have the fully conjugated system extending up to the oxygen with a series of p orbitals. Let's go over the mechanism for the tautomerization of a ketone or aldehyde to a enol. The mechanism is drawn differently depending on whether it's acid catalyzed or base catalyzed. Recall that in mechanisms that are acid catalyzed, we typically have intermediates that are either neutral or have a full positive charge. Base catalyzed reactions typically have intermediates that are either neutral or have a negative charge. So when you're drawing a mechanism, make sure that the structures that you draw are consistent with the conditions being employed. So if we have an acid in solution, it makes sense that the acid will donate a proton to the ketone. And it can do so by protonating one of the lone pairs on the oxygen of the carbonyl. That gives us this resonance stabilized cation, where the positive charge is delocalized between the oxygen and the carbonyl carbon. From here, water can take the proton that is located at the alpha carbon, and electrons can flow to form a pi bond, satisfying the carbon's electron deficient state in this resonance structure to form a pi bond between those 2 carbons. Notice the equilibrium arrows. This process of going from a ketone to an enol is entirely reversible, and you could draw a mechanism going back from the enol to the keto form. Let's look at the mechanism of tautomerization of a ketone to an enol under basic conditions. So if we have sodium hydroxide, that's a base, and it's very likely that it can pick up a proton from the alpha position. Eventually, we'll talk about how acidic these protons are. That can leave an anion at the alpha carbon that's resonance stabilized and partially delocalized up to the oxygen atom. And after protonation with water, we get to the enol structure. Now you might ask, why doesn't this hydroxide, which is a strong base, but is also a strong nucleophile, why doesn't it attack the carbonyl carbon? We saw that before in a previous chapter where we formed a hydrate, and the first step was nucleophilic attack of hydroxide to the carbonyl carbon of a ketone. And that, of course, that can happen, but that is also a reversible reaction. While there, in some cases, right, we will have nucleophilic attack on the electrophilic carbon, leading eventually to a hydrate. That process is reversible. That gets us back to the keto form. And sometimes hydroxide can act as a base instead of a nucleophile. And when it does that, it will take the hydrogens on the alpha carbon because they're fairly acidic. And again, we're going to talk about that in a little bit. So it's safe to assume that if you have a ketone or aldehyde, some fraction of those molecules will exist in the enol form. And if we look at the resonance structures of an enol, we have two resonance contributors, and one shows us that there is a partial negative charge on the alpha carbon. So essentially, we've created a nucleophile at the alpha carbon, and we can utilize that nucleophile to react with a variety of electrophiles, which we're going to see with the reactions in this chapter. This is an electrostatic potential map showing you that while the oxygen is electron rich, the alpha carbon actually is also electron rich. So let's practice in the mechanism of the reverse process, right? So from an enol, going back to the keto form, let's draw the mechanism that would be acid catalyzed and a separate mechanism that would be base catalyzed, again, to reverse the process and go from an enol back to the keto form. Go ahead and pause the video to draw it, and then we'll go over it. Okay, let's go ahead and go over this problem. So I'm going to do the acid catalyzed conditions first. So whenever you're drawing the acid catalyzed conditions, go ahead and draw your starting material along with some hydronium ion. Now we know that under acid present, it's very likely that the acid will donate a proton and protonate our substrate. Let's think about where we should protonate. Should we protonate the oxygen, right? Or is there another position that we might want to protonate? Well, it's possible to protonate the oxygen. That doesn't actually lead us anywhere, and that process or proton transfer is reversible. So it doesn't actually help us to protonate the oxygen. But if you recall, looking at the resonance contributors of an enol, we saw that the other resonance contributor of an enol shows us that the alpha carbon has a partial negative charge and is nucleophilic. So it makes sense to also protonate the alpha carbon. So if we use this pi bond as our nucleophile, we can go ahead and pick up a proton at the alpha carbon. That's going to leave a positive charge at the carbon attached to the oxygen. This is resonance stabilized. Notice the resonance arrow that I'm drawing here. And if we want to show resonance, we should draw in our resonance arrow. The pattern is lone pair adjacent to a positive charge. Okay, there's the other resonance contributor, where now the oxygen has the formal charge. So we know that the true structure is that the oxygen and the carbon attached to it share the positive charge. We're very close to the ketone. All we have to do is do a final proton transfer to remove this proton. Water is the best base that we have in solution. Go ahead and draw a water molecule to come and pick up that proton. Notice that we also regenerate hydronium ion in that step, and therefore all we need is catalytic acid because it gets used and regenerated. Let's look at the mechanism. We have a base catalyzing. I'm going to go ahead and draw out the starting enol again. And some hydroxide. With reaction with a base, it's likely that the base will deprotonate our substrate. The most acidic hydrogen is the one attached to the oxygen, so it's very likely that the base will remove that proton. Notice that that actually gives us an enolate, and enolates are resonance stabilized. So we can go ahead and draw out a resonance contributor. The pattern I'm going to draw is the allylic lone pair. This shows us that the negative charge is localized between the oxygen and the alpha carbon. And both of those have a partial negative charge as a result. Notice that we're very close to the keto form in this tautomerization. And all we need to do is protonate the alpha carbon to get to the keto form. Water is the best acid in solution, so I'm going to go ahead and draw some water in. That will provide a proton to get to the product, which is the ketone. Notice that we also form some hydroxide in this step. So again, only catalytic base is needed because it gets used and regenerated in the mechanism. Let's go back to our slides and move on. Let's do another practice problem. The question is, how many enols can be formed from 3-methyl-2-butanone? So this is partially a question of nomenclature, right? So we have to remember how to draw ketones, and notice that it is a ketone from the "-one" in the name. And then once we have the correct structure drawn, to think about how many enols might be formed from that structure. Recall that ketones have 2 alpha carbons. So that should give you a clue as to potentially drawing more than 1 enol. Go ahead and pause the video and try it for yourself, and then we'll talk about it. Okay, so again, the first part of this problem is figuring out how to draw this structure. By the way, this is a very common thing to see on the ACS final exam. They'll often combine some IUPAC nomenclature into the problem when they're actually asking you for a reaction or something else involved with that structure. Okay, so first I'm going to look at the parent, which is a 2-butanone. So I'm going to start by drawing 4 carbons, right, and a ketone at carbon number 2. Then I'm going to look at the substituent, which is a 3-methyl group. So if I counted from this side, 1, 2, 3, put the methyl group there. Okay, so hopefully you got to this structure and maybe you identified that there's more than one alpha carbon. Ask yourself, do both alpha carbons have at least one hydrogen attached? The answer is that they do. This one has 1 hydrogen attached, and this structure, or this alpha carbon, has 3 hydrogens attached. So we can form enolates by transferring one of these protons to the oxygen and forming a double bond in this direction, or transferring one of the oxygens on this alpha carbon to the oxygen and forming a double bond in this direction. So the 2 enols that can be formed. We form an enol with the alpha carbon on the right. We'll make a double bond between those 2 carbons and an OH group where the carbonyl was. And also we can go the other direction with our double bond, right? Placing it between the alpha carbon on the left and the carbonyl carbon along with an OH group. Right? So this is 1 enol and 2 enols that can be formed. So eventually when we talk about reactions, we're going to need to think about which substrates can potentially form more than one enol or enolate intermediate and what the conditions favor, right? If one or the other enolate is favored in those conditions. Okay, moving on, let's talk about if you're in the presence of a full equivalent of a strong base, then an enolate forms. So you might be confused because we just talked about a strong base forming an enol, right, with hydroxide ion. But remember that that was only a catalytic amount of a strong base. When you have a full equivalent of strong base, then you get full conversion of the aldehyde or ketone to an enolate intermediate. Okay, recall that an enolate is different from an enol because of the full negative charge on the intermediate. Where the enol was neutral, an enolate has a negative charge. It's delocalized between the alpha carbon and the oxygen. Because of the full negative charge, the alpha carbon is more electron rich and a stronger nucleophile than an enol's alpha carbon. So that negative charge, as I mentioned, is delocalized between the oxygen and the alpha carbon. So when you treat an enolate with an electrophile, the bond between the substrate and the electrophile might occur between the oxygen and the electrophile or the alpha carbon and the electrophile. We call this oxygen attack versus carbon attack. Right? And we're calling it attack because this is the nucleophile, and we say that the nucleophile attacks the electrophile. So which process is typically favored? As it turns out, enolates typically undergo carbon attack, which can be drawn in one of 2 ways mechanistically. If you use this resonance contributor, then you need to show 2 arrows, to form the product. And if you had drawn this resonance contributor, only 1 arrow is needed to form the product. Either one of these resonance contributors is acceptable, and that's because, of course, we typically just have to draw one or the other resonance contributor with the full knowledge that the lone pair in question is delocalized. The majority of the reaction in this chapter involve enolates, so it's going to be very common to show a nucleophilic attack of an enolate. Recall that we talked about the alpha carbon, the beta carbon, and the gamma carbon. All of those carbons may have hydrogens attached to them. However, only the alpha protons are acidic. And that's because removal of one of these alpha protons results in an enolate, which is a resonance stabilized conjugate base. Recall that resonance stabilizes structures. So because we're able to form a resonance stabilized conjugate base, we'll be protonating one of these two hydrogens attached to the alpha carbon. That makes these alpha protons more acidic than the protons at the beta carbon or the gamma carbon. Right? Removal of one of these would lead to a localized lone pair, right, which is not as stable as a delocalized lone pair that exists in an enolate. Let's do a practice problem. Right? The question says, draw both resonance forms of the enolate that can be formed from this aldehyde. Go ahead and work on this problem, pause the video, and then we'll go over it. Okay, so recall that there are two resonance forms of enolates. And it doesn't matter which one we form first, because we can always convert one to the other through drawing resonance. So if we first start with the resonance contributor where the lone pair is on the carbon, the alpha carbon, right, that would be one resonance contributor. And the other resonance contributor right, moves the lone pair and the negative charge to the oxygen. So these are the two resonance contributors, and it doesn't matter which one you use when drawing mechanisms, right? The difference is when you're doing a nucleophilic attack, with this one, it would only involve one arrow from this, right, substrate, and then we would need two arrows to do a nucleophilic attack on the substrate from this resonance contributor. All right, let's look at the acidity of these hydrogens at the alpha carbon. Here we have three different structures. Two are ketones. The last one is an aldehyde. All of them have carbonyls, where there's an alpha carbon with a hydrogen highlighted in red. If we look at the pKa value, it ranges between about 17 and 19. So recall that that is about as acidic as water in this case, and slightly less acidic for the alpha position of a ketone. It's good to keep those pKa values in mind as we start talking about the appropriate base that needs to be used to form an enolate. Let's look at acetaldehyde as an example. Recall from the table on the previous slide that the pKa of the alpha proton of acetaldehyde is 16.7. One common mistake is that students think that the hydrogen attached to the carbonyl is acidic on an aldehyde, but the hydrogen attached to the carbonyl of an aldehyde is not acidic like the hydrogens attached to the alpha carbon of an aldehyde. And the reason why is if we deprotonate this and put a lone pair and a negative charge on this carbon, it is not resonance stabilized and delocalized. So the carbon has a full localized lone pair and negative charge and is not stable. And as a result, this hydrogen is not acidic. So be careful not to deprotonate the aldehyde hydrogen. Okay, let's look at the choice of ethoxide as a base for this proton transfer. If we draw out the products of the proton transfer, right, they've done just a simple proton transfer, delivering the electrons from this bond as a lone pair on the alpha carbon. So they've chosen to draw this resonance contributor of the enolate, but it wouldn't have mattered if they had moved electrons all the way up to the oxygen and drawn the other resonance contributor. It would not change the values in this acid-base equation at all, which resonance contributor is drawn here. The conjugate acid in this reaction is ethanol, and ethanol has a pKa of about 15.9. Notice that these pKa values are not significantly different. And so what that tells me is that sodium ethoxide is not a strong enough base to fully deprotonate the alpha position of an aldehyde. And in fact, with a very similar pKa value, the approximate concentration of the enolate and the aldehyde in solution, right, is about equal amounts, or at least there's a significant amount of both the enolate and the aldehyde in solution. Even if it's not 50-50, we know that both are present still in solution. So it's a partial conversion to the enolate instead of a full conversion to the enolate. And that's going to become important because later on in section 21.3, we're going to talk about a reaction called the aldol reaction. And that reaction involves the enolate attacking another molecule of aldehyde to form a product. So when doing the aldol reaction, one would choose a base such as sodium hydroxide or sodium ethoxide, because the goal is to only partially convert the aldehyde into enolate and have a significant amount of aldehyde remaining at equilibrium such that these two can react together to form a product. Let's look at some other choices of base. Instead of ethoxide, let's look at hydride that might be supplied by, for example, sodium hydride. Hydride is a very strong base, and it can deprotonate the alpha position of an aldehyde or ketone to form an enolate. When it does so, the conjugate acid is hydrogen gas, which if allowed to bubble out of solution will drive the reaction forward to form more enolate. And there's a significant enough difference in pKa value between H2 and the alpha proton of an aldehyde or ketone, such that it's essentially exclusive and full conversion to the enolate, and there is no more aldehyde in solution. So we say that it's essentially irreversible. Another base that we could use is a base that's called LDA. LDA stands for lithium diisopropylamide, and it's formed when diisopropylamine is treated with N-butyllithium. This forms a very strong and bulky base, which is commonly used as a base in reactions. One of the great things about LDA is the fact that the nitrogen atom, while very strongly basic with a full negative charge, also contains these bulky isopropyl groups. This is going to make this nitrogen atom non-nucleophilic, and it will only function as a base and not as a nucleophile, which might lead to undesired side reactions. Again, LDA is commonly used. It's a strong, bulky base, and in the presence of an aldehyde that has an alpha hydrogen, an acid-base reaction can take place where the nitrogen atom takes a proton from the alpha position. We form the enolate, and we form the protonated amine. We look at the pKa difference between the alpha proton of acetaldehyde and the amine. There is about 19 pKa units difference, right, between 17 and 36. So this is essentially an irreversible reaction. So if we want to fully convert a aldehyde with at least one alpha proton to an enolate, we might choose sodium hydride or LDA as the base instead of a weaker base such as sodium hydroxide or sodium methoxide or ethoxide. Let's compare the pKa of the alpha hydrogen of acetaldehyde with the pKa of the hydrogens interior to two carbonyls and a 1,3 diketone. These hydrogens are actually more acidic than typical alpha hydrogens. They are attached to the alpha carbon of a ketone, but notice how they are attached to the alpha carbon of two ketones. So that makes them more acidic than typical hydrogens in the alpha position, and the pK is more like 9. We can see the stability of the conjugate base by drawing the resonance structures, where the lone pair negative charge are delocalized between the alpha carbon and both oxygens. Having two oxygens contribute to the resonance stability makes this structure more stable than a typical enolate, and as a result lowers the pKa of these protons that are interior to two carbonyls instead of one. Because these hydrogens are more acidic, sodium hydroxide, methoxide, or ethoxide is actually a strong enough base to almost completely and irreversibly deprotonate the alpha position, but not just any alpha position. Recall that the alpha position that has the hydrogens that are most acidic are the interior to two carbonyls. So we would not want to show deprotonation of one of these terminal methyl groups. While they are alpha to a carbonyl, they're only alpha to one carbonyl. The pKa of these hydrogens at the end of the molecules is more like, again, 18, 19. So the hydrogens inside are much more acidic. So sodium ethoxide would selectively deprotonate a hydrogen in the center of this molecule, forming what we would call a doubly stabilized enolate. With a pKa difference between the acid and the conjugate acid of about 7, that is significant enough that there's significantly more products than reactants in solution. There would be no need to use a strong base like sodium hydride or LDA to form this enolate. Essentially, it would be overkill because a much more simple base like hydroxide or ethoxide is sufficient to produce the enolate without need for a stronger base. So let's review. In summary, if you're dealing with a simple aldehyde or ketone and treating it with a stoichiometric amount of a strong base, such as sodium hydroxide or sodium ethoxide, right, we're going to convert part of the ketone to an enolate, but a significant amount of the ketone or aldehyde will still remain in solution. And the reason why is even though this is considered a strong base, it's not a strong enough base to completely deprotonate the alpha protons because the alpha protons are not that acidic. And this is not as strong a base as some other choices. If we wanted to irreversibly and completely deprotonate the alpha position and only have the enolate in solution, a stronger base like sodium hydride or LDA would be used. Sodium hydroxide or sodium ethoxide, in contrast, does completely deprotonate the alpha position of a 1,3 diketone to form the doubly stabilized enolate. In this case, a strong base like sodium hydride or LDA is simply not necessary to get full conversion to the enolate. Let's do a practice problem. The question says, draw the enolate that is formed when each of the following compounds is treated with sodium ethoxide. In each case, predict whether a substantial amount of starting ketone will be present together with the enolate at equilibrium. Go ahead and pause this so you can work on it, and then we'll go over it. Okay, let's go ahead and go over that. When we are treating with ethoxide, recall that the hydrogens interior alpha to two different carbonyls are much more acidic than the alpha position, where the conjugate base is only localized up to one oxygen. So with these hydrogens being more acidic with a pKa of 9, we should selectively deprotonate one of the two hydrogens on this central carbon. showing the mechanism there, I'm just going to go ahead and leave the lone pair on the alpha carbon. And if I wanted to, I could have shifted the electrons all the way up to the oxygen, but it's optional. And just because I'm drawing a mechanism, I'm going to go ahead and add in all the lone pairs as well. So recall that the pKa difference is about 7 between the starting material and ethanol, which is the conjugate acid. So this is essentially irreversible, right? And we would not expect a substantial amount of the starting ketone together with the enolate at equilibrium. So this we're going to say is not present at equilibrium. Let's look at this structure where we only have one carbonyl. Notice that it is symmetrical, so the alpha positions are equivalent. We don't need to worry about selecting hydrogen on either side. They're essentially going to produce the same thing. Let's draw in some ethoxide base. And in this case, I'm going to show you how to push electrons all the way up to the oxygen, drawing the other resonance contributor of the enolate directly. You protonate the alpha position, and then instead of depositing these electrons as a lone pair on the alpha carbon, form a double bond between the two carbons, and then push the electrons from the pi bond, the carbonyl, up to the oxygen. So that goes directly to this resonance contributor. So the question is, right, what is going to be present at equilibrium? I am going to draw a reverse arrow here because we're not going to exclusively get only enolates at equilibrium, right? Because the pKa difference between the conjugate acid ethanol and the alpha proton of this ketone is not as significantly different, right? So we're going to say both the enolate and the ketone are present at equilibrium. Just for clarity, I'll go ahead and draw in the conjugate acid. So in each case, we form some ethanol. Right, let's do another practice problem. In this case, it's a question and it asks, can you think of any aldehydes or ketones which cannot form an enolate? So go ahead and pause it and see if you can draw a structure of an aldehyde or ketone that is an enolate would not be able to be formed. Okay, let's go ahead and go over this question. So recall that aldehydes and ketones have alpha carbon. And in order to form an enolate, we need to have at least one hydrogen attached to the alpha carbon. So if we come up with a substrate where there is not a hydrogen attached to the alpha carbon, then you will not be able to form an enolate from that specific aldehyde or ketone. So for example, perhaps I put in benzene ring here, right? Now the alpha carbon does not have any hydrogens attached and no enolate can be formed using this aldehyde. What about a ketone? Let's start with a simple ketone. Right? As long as there is a hydrogen at one of these two alpha carbons, an enolate will be possible. So we'd need to come up with a structure where there are not any hydrogens attached to these two alpha carbons. So perhaps you might have thought of like a tert-butyl group. Maybe we would put two tert-butyl groups. Now the two alpha carbons, neither one has a hydrogen attached, so no enolate can be formed from this ketone either. There's a variety of other potential answers you might have come up with. And if you have any question about whether or not it would work, go ahead and let me know in office hours or send me an email. And I'll be happy to take a look. All right, let's move on to section 21.2, alpha halogenation under acidic conditions. So recall that under acidic catalytic acid conditions, ketones and aldehydes, where there's at least one hydrogen attached to the alpha carbon, can form an enol. And also recall that that enol is nucleophilic at the alpha carbon. So because it becomes a nucleophile in its enol form, it can react with electrophiles. One such electrophile is bromine. We've seen bromine act as an electrophile before. Back in the first semester of this course, we saw bromine react with alkenes to form anti-dibrominated products. So in this case, bromine will act as an electrophile, and the nucleophilic alpha carbon will attack it and will end up with an alpha bromo ketone. This works also with chlorine and iodine, but fluorine is not a polarizable enough electrophile, and the reaction does not work well with fluorine. Again, acidic conditions mean that an enol can be formed, and the alpha carbon of the enol is the reactive intermediate. So let's look at the mechanism. Starting with the ketone, under catalytic acid conditions, we saw the reaction before where we convert the ketone to its enol tautomer. Once it's in the enol tautomer, we have the exposed the nucleophilic alpha carbon. So the nucleophilic alpha carbon can then attack one of the bromines, kicking off the other bromine as bromide. That leaves this intermediate where there's a proton attached to the carbonyl, which can be easily removed with water, and the product then is an alpha bromo ketone. What happens if you use an asymmetric ketone? Right? Let's look at this cyclohexanone derivative where we have one alpha carbon has two hydrogens and the other alpha carbon only has one, and there's a methyl group attached there. So the question then is, where does the bromine end up? Does it end up on this more substituted position, alpha carbon, or does it end up on the less substituted alpha carbon? Well, it turns out that the major product places the bromine at the more substituted position. And that's because it goes through the more stable enol intermediate. Recall that alkenes are stabilized by substituents. This alkene is tetrasubstituted, and this alkene is only trisubstituted because there's one hydrogen here, so that doesn't count. So as a result, the more substituted, more stable alkene is going to be formed in greater amount, and that ends up with the nucleophile placed at this alpha carbon, leading to the bromine at that position in the major product. We can actually expand this to synthesize an alpha beta unsaturated ketone. So the reason why I call this an alpha beta unsaturated is because this is the alpha carbon to this carbonyl, this is a beta carbon to this carbonyl, and there's a pi bond. So pi bonds, as you know, are units of unsaturation. So one of the ways we can name this is calling this an alpha beta unsaturated ketone. So recall the first step with catalytic acid and bromine. We'll place a bromine regioselectively at this alpha carbon, and then pyridine will do an E2 reaction, removing a proton at this beta carbon and kicking out the bromine as a leaving group, generating an alkene between those two carbons. If you remember the structure of pyridine, right, it's essentially a benzene ring where one of the carbons is replaced by nitrogen. That nitrogen has a lone pair. That nitrogen's lone pair is considered a non-nucleophilic base. So it's great to do E2 reactions where we want the substrate added to act as a base and not a nucleophile. Other bases that can be used for the elimination are bases like potassium terbutoxide, again, a non-nucleophilic base, or lithium carbonate, same thing. Let's do a practice problem. This is a synthesis problem, so it's going to involve multiple steps. So go ahead and try to identify the reagents that can be used to accomplish the following transformation. Don't forget that we just talked about alpha halogenation, so see if you can incorporate that into your synthesis. Again, go ahead and pause the video, and when you're ready, resume and we will go over the answer. Okay, so recall that we have been talking about alpha halogenation, right? And if we have a carbonyl, we'll be able to halogenate on this alpha carbon and then form a pi bond through an E2 elimination reaction. So right now we only have the alcohol, but we of course know that we can oxidize this alcohol to an aldehyde. And aldehydes and ketones are the starting material to form enols and enolates, which are the intermediate that we're studying for the reactions in this chapter. So again, oxidation of a primary alcohol to an aldehyde. You can use PCC, which is pyridinium chlorochromate. And from here, we can do a two-step process where we alpha halogenate, catalytic acid, bromine, followed by either pyridine, potassium terbutoxide, or lithium carbonate. And that will again place a bromine at the alpha carbon, and then an elimination will lead to the pi bond that we see here. Okay, let's move on to a named organic reaction. It's called the Hell-Volhard-Zielinski, or the HVZ reaction, and it brominates the alpha carbon of a carboxylic acid. The conditions used are, in the first step, bromine and PBr3, and in the second step, just simply water or a hydrolysis. Notice that the yields of these reactions are quite good. Let's start with a carboxylic acid. This is drawn as just a generic carboxylic acid, but notice they included the alpha carbon because we're going to need to utilize the alpha carbon to introduce a bromine at that position in this reaction. So while we're not going to go over the entire mechanism, it's thought that the PBr3 converts the carboxylic acid to an acid bromide in this case. And this is in equilibrium with its keto to enol form, creating a nucleophile at the alpha carbon. The nucleophile could then react with bromine, similar to the last reaction we just talked about, to place a bromine at the alpha carbon. And then acyl bromides are not stable in the presence of water. So once water is added, just like an acid chloride, an acid bromide or acyl bromide will be hydrolyzed back to a carboxylic acid. Alpha halogenation can also be achieved under basic conditions with sodium hydroxide in the presence of bromine. And we're going to use a stoichiometric amount of sodium hydroxide. So an enolate is the reactive intermediate. Hydroxide will deprotonate the alpha position of a ketone, creating an enolate, which then does a nucleophilic attack on the bromine, kicking out bromide and generating the alpha brominated ketone product. This reaction under basic conditions is actually not as ideal as the reaction under catalytic acid conditions, because under basic conditions, polyhalogenation typically results, right? So instead of getting just one bromine on the alpha carbon, unfortunately, all of the alpha hydrogens that are present will likely be brominated. In this case, the alpha carbon on the left is blocked by two methyl groups, so we don't expect to put any bromines here. But there are still two hydrogens attached to the alpha carbon on the right, and that can lead to a dibrominated product. So if this wasn't the product that you were looking for, you probably wouldn't want to use the reactions under the strong base and instead use the acid catalyzed conditions that we saw previously. The reason why polyhalogenation occurs is because once one bromine is added, there's still an acidic alpha hydrogen, and the deprotonation of that hydrogen is even faster than the deprotonation of the substrate, because that new enolate, where one bromine is already present, is even more stable due to the electron withdrawing nature of the bromine, helping to stabilize the enolate. Let's talk about the haloform reaction. The haloform reaction is the reaction of a methyl ketone. Notice that we have a ketone here, and on one side we have a methyl group. So that's what I am calling a methyl ketone. The methyl ketone gets converted to a carboxylic acid. Notice that the conditions are exactly what we were just talking about for alpha halogenation under with base present. So recall that this reaction has a hard time stopping by adding just one bromine, and that all of the alpha hydrogens will eventually get brominated because the product is even more reactive in the reaction than the starting substrate. So as a result, we're going to end up putting 3 bromines on this methyl group. Then sodium hydroxide will come in and do a nucleophilic attack, kicking off that tri-brominated methyl anion as a leaving group and eventually leading to a carboxylic acid. Let's look at that mechanism. So again, we're going to have 3 brominations of the alpha position of the methyl, leading to this tri-brominated alpha carbon. And then sodium hydroxide will then act as a nucleophile instead of a base, doing a nucleophilic attack on the carbonyl carbon. Electrons will get kicked up to the oxygen to avoid exceeding the octet on this carbon. That gives us this tetrahedral intermediate. Well, it turns out that once there are 3 bromines attached to this carbon, we can actually kick this out as a leaving group. So we can from this intermediate, we can regenerate the carbonyl and lose the carbanion as a leaving group. It's a reasonable leaving group because it's fairly stable, where the carbon anion electron density is being pulled by the 3 electronegative bromines attached to the carbon. That's going to reveal a carboxylic acid product. Remember that carboxylic acids have a pKa of 5, so they're pretty acidic. And even though this carbon anion is fairly stabilized by induction of the bromines, right, it is still basic enough to deprotonate a carboxylic acid. So the products before the acidic workup are the carboxylate and bromoform. And after the acidic workup, the carboxylate will be converted back to a carboxylic acid and potentially isolated at that point. So for this reaction, right, the haloform reaction, we can use bromine, chlorine, or iodine. And it is a useful reaction because essentially we're able to convert a methyl ketone to a carboxylic acid. Notice that we are losing a carbon in our carbon scaffold. So if you ever synthetically need to lose a carbon, right, one way to do that is potentially to use this haloform reaction. Some of you might have heard of chemical tests, and this is actually a chemical test, which was a test for certain functional groups that was widely used before other methods were brought forth that allowed for structure determination. Okay, so before the advent of NMR and other useful instruments that can help us determine structure, we sometimes determine structure through a variety of what are known as chemical tests. So the way this works is you could test for the presence of a methyl ketone by adding in sodium hydroxide and actually iodine instead of bromine, followed by an acidic workup. The products would be a carboxylic acid, and instead of bromoform, you would get iodoform, which is HCI3, right? And one of the reasons why iodine is used instead of bromine is because iodoform will precipitate out of an organic solvent as a nice bright yellow solid. So the iodoform, or the presence of a yellow solid in the reaction, was a positive indication that we had a methyl ketone in solution. The reaction works best if there aren't any other alpha protons. So if this R group was, for example, like a phenyl or a tert-butyl, where there aren't any other hydrogens attached to another alpha carbon. Because of course, if there was hydrogens attached to a second alpha carbon, those hydrogens would also be replaced with bromine, which might not be what is synthetically desired. Okay, let's do another synthesis problem as a practice problem. So I'd like you to go ahead and think about how you might convert this alkene to this ketone, right? And of course, whenever you're doing these practice problems within the chapter, think about how we can use the reaction that we just talked about, specifically potentially a haloform reaction, as a key reaction in this synthesis. So again, go ahead and pause, and we'll go when you're ready. Okay, let's go ahead and go over this. So you might be thinking about the fact that we actually don't need this carbon, right? It's not present in the product. Instead, there's a oxygen there, right? So we definitely do probably want to cleave this carbon-carbon double bond to form a carbonyl, right? And you might recall that we can use ozonolysis to do that. That might be a good starting place, right, to think about if there's any way we could proceed after getting a carbonyl instead of an alkene. So again, ozonolysis of an alkene to produce a ketone utilizes ozone, followed by a reducing agent such as zinc or dimethyl sulfide. Once we have this carbonyl, we're almost there to the product, but we do need to introduce another carbon somehow. We talked about the fact that we were just talking about alpha halogenation and the haloform reaction specifically. So maybe there's a way to utilize that in this synthesis. So let's think about, what if we use the haloform reaction to convert this methyl ketone to a carboxylic acid? Would that be helpful to get closer, potentially, to the product? Might seem counterintuitive to remove the methyl group and then reintroduce an ethyl group, but it actually can be a synthetically fairly straightforward process. So again, the conditions for the haloform reaction are sodium hydroxide and bromine, chlorine, or iodine. So it doesn't matter which one you choose, followed by an acidic workup in order to isolate the neutral carboxylic acid. This brings us back to our previous chapter where we studied reactions of carboxylic acid derivatives. So recall that if we want to react a carboxylic acid to form a ketone, it would be best to first convert the carboxylic acid to an acid chloride, because acid chlorides are much more reactive than carboxylic acids. And we do that using thionyl chloride. Once we're at the acid chloride, we can convert that to a ketone using a Gilman reagent. So because we want to add an ethyl group, we're going to go ahead and add a Gilman reagent where the copper is attached to ethyl groups. And that allows us to directly from an acid chloride to a ketone with whatever R group, right, is present in these parentheses. If you have studied this chapter in more detail, and perhaps you're looking at this for a second time, you might realize that there are other ways to convert the methyl ketone to an ethyl ketone, specifically through what's called the alpha alkylation reaction. I specifically didn't use alpha alkylation because we haven't covered that yet in section 21.2. But as you study this reaction, chapter further, you will note that there's other ways to go from a methyl ketone to an ethyl ketone. But this is one pathway that would work out, and it utilizes some reactions from this chapter and some review reactions from previous chapters. Okay, we're moving on to section 21.3, which is aldol reactions. So remember when we were talking about acid-base reactions, and we were treating aldehydes with hydroxide or an alkoxide like sodium ethoxide? An equilibrium formed where significant amounts of both the enolate and the aldehyde are present. And when that occurs, the enolate can act as a nucleophile and attack the aldehyde. And the product of that reaction is a beta hydroxy ketone or aldehyde, and it's called the aldol reaction, named after the product, which has both an aldehyde and an alcohol. And the reason it's not called a ketol is because it's much more common to do the aldol addition reaction with aldehydes than ketones, because a greater yield of products is obtained with aldehydes compared to ketones. So again, the reaction involves starting with an aldehyde. It should have at least one alpha hydrogen, conversion with base to an enolate that can then attack another molecule of aldehyde, and we'll see the mechanism eventually forming beta hydroxy aldehydes. So the mechanism first involves the base deprotonating the alpha proton to form an enolate. And then we mentioned, of course, that the enolate is nucleophilic at the alpha carbon, and we know that aldehydes are electrophilic at their carbonyl carbon. So a nucleophilic attack can occur between those, along with a resonance arrow to avoid exceeding the octet on this carbon. From here, we can protonate the alkoxide that results with the best acid in solution, which is water, to form the beta hydroxy aldehyde product. Notice the equilibrium arrows that are being used in the mechanism. All of these steps are reversible, and it's very possible to go back from the product to the reactants in this reaction. So it's a reaction that needs to be controlled through an equilibrium process. And just note that 2 of these aldehydes are required to form one aldol product. So with most organic reactions, the substrate is 1-to-1 with comparing the substrate and the product, right, in terms of mole ratio. But in this case, it is a 2-to-1 reaction, which is fairly uncommon in organic reactions. Okay, so for most simple aldehydes, for example, this is butanol, right? The equilibrium favors the aldol product. You can note about 3:1 for this, in this case, so a good yield of the beta hydroxy aldehyde product can be isolated. But for most ketones, the equilibrium favors the reverse reaction or the retro reaction. And that's because the product is not quite as stable due to increased steric hindrance here as a result of using a ketone instead of an aldehyde. So again, we talked about the fact that the reaction is reversible, and in reverse, we would call it a retro-aldol reaction. So the mechanism in reverse is simply forming the same intermediates as you would form in the forward direction. So again, the retroaldol is favored for ketones, so we're going to go ahead and take a product that's formed from reaction of two ketones, in this case acetone, to draw the reverse reaction. So in reverse, hydroxide, which again is both a strong nucleophile and a strong base, it can do several things to this substrate. Right? One thing it can do is it can do a nucleophilic attack on this carbonyl and maybe eventually form a hydrate with this carbonyl. And while that's happening in solution, that is not actually leading us back to two acetone molecules, so that's not what we're going to draw in our mechanism. What else could hydroxide potentially do? Well, there's a ketone here and it has alpha carbons. Those alpha carbons have hydrogens attached to them. As we know, those hydrogens are fairly acidic and can be deprotonated with a base such as hydroxide. So it's quite possible that hydroxide might deprotonate one of the hydrogens attached to these alpha carbons. But again, that process is also reversible. Again, act as a base, but instead of deprotonating the alpha position of the ketone, it could deprotonate the hydrogen attached to the oxygen in the product. That leads us back to this alkoxide intermediate, which can then essentially reform a carbonyl and kick out an enolate as the leaving group. So notice that we essentially broke this carbon-carbon bond, right, forming two molecules from one, and the leaving group is an enolate. And the reason why we can kick out an enolate is because it's fairly stable due to the resonance delocalization and stabilization of the lone pair and negative charge. If the enolate picks up a proton from water, we get back to the other ketone. So this is entirely a reversible process, both the forward and reverse directions. Let's do a practice problem. At this point, I would like you to predict the major product obtained when the following aldehyde is treated with sodium hydroxide. So always look at the section that we're in. We've been talking about aldol addition reactions. So we're going to be drawing the aldol addition product when two of these aldehydes are combined, right, to form one aldol product. Go ahead and pause. Okay, so we are going to be drawing the aldol addition product. And again, we know that we need to utilize two aldehydes. Right? So I'm just going to go ahead and draw a second substrate because it's a 2-to-1 reaction. One of the substrates will form the enolate, so it'll be deprotonated with sodium hydroxide. I'm not going to draw the full mechanism here because I wasn't asked to draw the mechanism. I was only asked to predict the major product. So I'm just going to go to one of the resonance structures of the enolate and just go ahead and directly form the enolate. And then I know that I'm going to be doing a nucleophilic attack between the alpha carbon of the enolate and the carbonyl carbon of the aldehyde. pushing electrons up to this oxygen, and after the acidic workup, we'll get an OH or an alcohol at that carbon. So what we can do here is just draw one, right? Draw our new carbon-carbon bond that we're forming in this reaction. And I can draw in the rest of the carbons and draw an OH. So if we just line these two aldehydes up, essentially one on top of the other, form an enolate from the top one, imagine the nucleophilic attack that takes place, right? And then draw the product that results. It's fairly easy to visualize. Make sure that you are getting a beta hydroxy aldehyde as your product, right? Because that is the product of an aldol addition reaction. It's not always drawn this way, so sometimes it might be drawn in a different fashion, but don't get too confused by that. For example, if I wanted to, I could redraw the structure and have it look like this. This is a more traditional beta hydroxy aldehyde where the functional groups are sort of horizontal, more traditional way to look at it, right? But those are really the same structure. Okay, so it's just sometimes we draw it this way because it's more easy to visualize how that forms using two aldehydes. Okay, so now let's talk about the aldol condensation reaction. Recall we were just talking about the aldol addition reaction, which produced the beta hydroxy aldehyde. So an aldol condensation forms when you heat the reaction mixture. So note that before, when we were doing the aldol reaction, addition reaction, we just used sodium hydroxide without any heat. If we want to convert the product, we can just continue with the sodium hydroxide treatment and heat the reaction up, or we could isolate the product and then switch to acid and heat that up. So either catalytic acid or base will convert the aldol addition product to the aldol condensation product. It's a condensation reaction because we have expelled a small molecule, in this case water, and formed a double bond. So how would we classify this product, right? Recall that the product would be called an alpha beta unsaturated aldehyde or ketone, in this case aldehyde, right? So if we want to get the aldol addition product, we would use sodium hydroxide at room temperature. If we wanted to go all the way to the condensation product, we would heat the reaction mixture up and, and expel water. Okay, so just to make sure everybody understands, right, the aldol addition reaction utilizes two aldehydes or ketones, but usually aldehydes, right, to form a beta hydroxy aldehyde product that can react further to give an alpha beta unsaturated aldehyde and expel a water when the reaction is typically when the reaction is heated, but there is an exception to that we'll talk about in just a minute. Recall the mechanism of aldol addition. So the first step is proton transfer, where the sodium hydroxide forms the enolate by deprotonating the alpha position of the aldehyde. The enolate then attacks another molecule of aldehyde that's still present in solution at equilibrium after the proton transfer. That leads to a beta alkoxide, right, to this aldehyde, which can be protonated using water, resulting in the beta hydroxy aldehyde product. The condensation reaction just reacts the addition reaction product further by utilizing an additional hydroxide to then deprotonate the alpha position between the aldehyde and the alcohol, forming a resonance stabilized enolate that then expels hydroxide in an elimination process as the leaving group, generating an alkene. So I want you to be careful here that when drawing the second part of the mechanism to get to the condensation product, make sure you draw this as a two-step process, because it is not thought to be an E2 reaction. An E2 reaction would involve hydroxide deprotonating the alpha carbon, forming an pi bond or alkene directly, and losing the leaving group all in one step. If the reaction were to be E2, we would see second order kinetics for the reaction, and we do not see that. Instead, we see first order kinetics. So it is thought that hydroxide, and also concentration of hydroxide has no effect on the rate. So it is thought that hydroxide is not involved in the rate determining step, and it is involved in proton transfer just to form an enolate, and then the rate determining step is the elimination step, kicking out hydroxide and forming the conjugated product. The mechanism is, going back, excuse me, the mechanism here is not, again, it's not E2, right? And it is first order, right? So it's a type of E1 reaction, but we don't call it just by itself an E1 reaction, because an E1 reaction that we talked about last semester involves the formation of a carbocation by loss of a leaving group. So notice that we did not form a carbocation intermediate. So this is not a traditional E1 reaction either. So because it has first order kinetics, and this is the molecule by which the rate depends on, right? And it's not a carbocation. We call it an E1CB reaction. And the CB stands for conjugate base. So it's an first order reaction, which is where the 1 comes from in E1. And the CB stands for the conjugate base. This is the conjugate base of the reactant, which is acid in this acid-base reaction. Okay, so when it's possible to form more than one stereoisomer as a product, for example, an E-alkene or a Z-alkene, you can also think of this as a transalkene and a cis-alkene, then the more stable, less sterically hindered product is typically the major product. So traditionally, when we draw the product, we'll draw the E or the transalkene. It's typically more stable than the Z or the cis-alkene. Remember, I talked about there would be an exception to forming the condensation product. Typically, in order to go from the aldol addition product, which would be this one, to the condensation product, which is this one, we would need to heat the reaction. Right? This is an exception where it's actually difficult to isolate the aldol addition product in this particular aldol reaction, because the aldol addition product very easily converts to the condensation product through loss of water. And the reason why it's so easy to do the second part of the mechanism and go to the condensation product is because in this case, due to the phenyl rings, we have a extended conjugated pi system, right? So we have p orbitals at every single carbon all the way around this aromatic ring. There's p orbitals on the carbon and oxygen here, neighboring p orbitals on these two carbons, and then it's also in conjugation with this second aromatic ring. So there's an extended conjugated pi system, which is very stable. And as a result of this being so stable, this readily converts to the condensation product, even without heating the reaction. Remember, we talked about the fact that the yields are low for the aldol reaction, addition reaction, with starting from ketones, right? Because it's an equilibrium process and the retro aldol is favored with ketones due to the product being not very stable due to steric hindrance. However, if we heat the reaction to go past the aldol addition product all the way to the condensation product, the yields increase substantially. And that's because by eliminating this alcohol group, we actually get rid of a lot of the steric hindrance in the product, making this much more stable. And as a result, the equilibrium tends to form that. Okay, let's take a break to do a practice problem. Draw the condensation product obtained when the following compound is heated in the presence of sodium hydroxide. So again, we're in the aldol condensation section. Right? So we're going to be drawing an aldol condensation product, which is an alpha beta unsaturated aldehyde or ketone. In this case, we're starting with a ketone, so it will be an alpha beta unsaturated ketone. Right? We're using a base and we're heating it, so it will go all the way to the condensation product. So go ahead and pause and see if you can come up with the structure. Okay, let's go ahead and go over it. So there's a little trick to drawing the products as well. Again, we're only expected to draw the product. We're not expected to draw the entire mechanism because it didn't ask for that. The one thing you can do is line up the alpha carbon, right, with another molecule and essentially point the carbonyl of the second ketone directly at that alpha carbon, right? So then it would look like this. And the reason I've done that is so that we can essentially circle the carbonyl and the alpha carbon, and we're going to be forming a double bond between these two carbons and eliminating this hydrogen, this oxygen, and it will eventually become water. So we can visualize it that way. It's actually pretty easy to draw the product. We'll just go ahead and draw an alkene there and then connect it to the rest of the molecule. So that is the aldol condensation product. Again, note how it's an alpha beta unsaturated ketone. And that is formed when we heat, right, in the presence of hydroxide, or you could use acid. All right, let's start talking about what we call crossed aldol reactions. Crossed aldol reactions utilize two different aldehydes instead of two of the same aldehyde to produce the aldol product. Right? So it's also sometimes called a mixed aldol reaction. So in this case, we've mixed two different aldehydes. So this is known as acetaldehyde, or also known as ethanal. And then this aldehyde is known as propionaldehyde, also known as propanal. And if we mix these two together with some sodium hydroxide, we're going to end up with a complex mixture of products. And that's because both of these aldehydes could potentially form an enolate because they both have alpha carbons with hydrogens attached to them. So we have the possibility of either forming this enolate or this enolate. And then these two enolates can then react with either the starting aldehyde that formed that enolate, right, or the other aldehyde. And so we have this situation where the two enolates formed react with two different aldehydes, and there's four unique situations here where the aldol reaction can occur, forming four different products. This would not be a desired reaction to do for an organic chemist because we would never want a complex mixture of products because they would likely be very difficult to separate. So this is not a synthetically useful process. But there are ways to do synthetically useful crossed or mixed aldol reactions. So what are the ways we can make this process practical where we use two different substrates instead of forming a dimer with one substrate. One way to do it is if one of the substrates is relatively unhindered, meaning it makes a great electrophile, and it does not have any alpha protons. Notice that formaldehyde does not have an alpha carbon with hydrogens attached to it. So this is another example of an aldehyde, which cannot form an enolate, right? And that's an advantage for this crossed aldol reaction because the only aldehyde that can form an enolate is the propionyl, or also known as propanol. So only one enolate is possible in this solution. And then, of course, that enolate could attack another propanol, but recall that formaldehyde is also present, and because there's two hydrogens and no carbon-based groups, this carbonyl carbon is not as sterically hindered and more exposed. In addition, it's more reactive, so this is more electrophilic. These carbon-based groups are stabilizing the positive charge through hyperconjugation. So without one of those carbon-based groups stabilizing the positive charge, this carbon is more electrophilic. So it's successful then to form an enolate with this aldehyde and have it then preferentially attack the other aldehyde, leading to a successful cross-aldol product. Here's another example where we can perform a successful crossed aldol reaction. Here we have two different aldehydes being used, right? Notice that benzaldehyde, again, does not have any alpha protons, right? So we cannot form an enolate from the substrate, which limits the enolate only forming from the blue aldehyde. And then benzaldehyde is pretty sterically unhindered because this might look like a big bulky group, but recall that the entire thing is planar. So it's actually not very sterically hindering for a nucleophile to come in and attack this carbon. So as a result, we can form a successful cross-aldol addition reaction. However, this is placed in brackets because, again, with the phenyl group here, it's hard to isolate the aldol addition product because it directly goes to the aldol condensation product because of the stability of the extended conjugated pi system. Here is another example of a successful crossed aldol reaction. Notice that in the first example, we were using sodium hydroxide. And in this case, we're going to end up using a stronger base, recall LDA, which is lithium diisopropyl amide. A lithium diisopropyl amide will deprotonate the alpha position of a ketone or aldehyde, forming an enolate. And then if we form this at low temperature, right, so that it's fairly stable, right? So it's usually formed at -78 degrees, so very, very cold temperature. And then we add the second aldehyde in a dropwise fashion, kinetically faster for the enolate to attack the aldehyde than it is for the enolate to deprotonate the alpha position of the other aldehyde, essentially forming two enolates in solution. So luckily, the nucleophilic attack on this carbonyl carbon of the aldehyde is faster, and we're able to successfully do this crossed aldol reaction, forming the beta hydroxy keto product. All right, let's do a practice problem. This is a beta hydroxy keto product. So when you see that, you should be thinking, I can form that from an aldol reaction. And notice that does not look like it was a dimer. So we need to do a crossed aldol reaction to form this. So think about how you can successfully do a crossed aldol reaction to produce the following compound. Go ahead and pause. Okay, let's go ahead and go over it. Sometimes it's helpful to draw in a little alpha and beta, and then think about what carbon-carbon bond we're forming in this reaction. We're actually going to form the carbon-carbon bond between the alpha and beta carbon. So then that simplifies right? Thinking retrosynthetically, that simplifies to the left side being the enolate, right? And then the right side being the electrophile, so the nucleophile and the electrophilic carbon. So we're just going to convert that, that alcohol back into an aldehyde, breaking this carbon-carbon bond in a retrosynthetic process. So we need to be careful because we're using a ketone and an aldehyde, and both of them have alpha carbons that have hydrogens attached to them. So there's the potential to form two different enolates here. So when that's the case, we need to utilize example 2 from the previous slides, or method 2, using LDA instead of using sodium hydroxide. So to form this enolate, we would take the ketone. We would add LDA, typically at a very cold temperature. So sometimes it might be mentioned negative 78 degrees Celsius. We usually do that. Form the enolate at a low temperature. And then dropwise add in the other organic component to that. And of course, there would need to be an acidic workup. And that would produce the product. Now that I think about it, I actually think that typically water is shown as the proton source for this. So I think the book does not use the acidic workup as part of the reagents to be drawn over the arrow. So I'm going to go ahead and delete that. Okay, so we can also do what's known as an intramolecular aldol reaction. If we essentially have two ketones or aldehydes tied together as a diol. Right? So essentially what we can do is treat with sodium hydroxide and heat to get the aldol condensation product. And in this case, you're actually forming a ring. So one of these ketones converts to an enolate using the base. And then there's a nucleophilic attack that occurs intramolecularly. And 5 and 6 member rings form great yields using this reaction. So this is not really different from any other aldol condensation reaction. It's just done intramolecularly as opposed to intermolecularly like we've been looking at before. Let's go ahead and do a practice problem. Practice drawing a reasonable mechanism for this transformation. So again, you're going to work on forming the enolate from one of the ketones, and then doing a nucleophilic attack, and then continuing the mechanism until you get to the alpha beta unsaturated condensation product. So go ahead and pause and then resume when you're ready. Okay, so the goal of this problem is to think about doing the reaction in an intramolecular fashion. So we know that technically all of these carbons that I'm pointing to right now are all alpha carbons, right? So all of the hydrogens attached to them are acidic. The hydrogens interior are not more acidic than the hydrogens that are at the terminal ends of the molecule, because this is not a 1,3 diketone, this is a 1,4 diketone, right? So an enolate formed from deprotonation of an interior methylene is not doubly resonance stabilized, so it's not more stable than deprotonating of the protons at the terminal end of the molecule. If we were to deprotonate here, which will definitely happen in solution, and then attack the other carbonyl, we would be forming a 3-membered ring. Remembered rings are unstable, and so that's not a likely reaction to take place. What's much more likely is to deprotonate one of the terminal ends and then do an intramolecular nucleophilic attack, which will form a 5-membered ring, which is a much more stable ring. So the first step is going to be deprotonation using sodium hydroxide. And again, looking at this kind of gives us an idea of where we should do that deprotonation. Go ahead and draw in one of the hydrogens attached to the terminal carbon. So I'm going to show a proton transfer. Again, you can leave these electrons as a lone pair on this alpha carbon with a negative charge, or you can move the electrons all the way up to the oxygen. Notice that they did leave the lone pair and the negative charge on the carbon. Right? So just to show you that you can do it either way, I went ahead and moved the electrons all the way up to the oxygen. And it doesn't matter which one of those two you do, they essentially mean the same. Forming an enolate, and I'm actually going to try to make it look kind of like this so I can make it easy for you to visualize the nucleophilic attack. So from here, because I chose to draw this resonance form of the enolate instead of this one, you need to push electrons starting from the lone pair on the oxygen to then do the nucleophilic attack on the other carbonyl carbon. This is our ring forming step, right? So we are forming a 1, 2, 3, 4, 5 member ring. So go ahead and sketch out a 5-member ring here. We formed a carbonyl at this carbon in that step, so I'm going to go ahead and draw that in. And then the carbon that's being attacked is this one, right? And it contains both an oxygen with a negative charge and a methyl group. Right? At this point, we need to protonate this to get the aldol addition product, and then we'll take that aldol addition product and react it further to get the aldol condensation product. Best acid in solution when we're using base is water. So I'm going to go ahead and draw in a water molecule nearby so that I can pick up a proton from water. And now we're at the aldol addition product. And because we're heating it, we don't stop there, and we go on to do the second part of the mechanism, which is the condensation. That involves first deprotonating the alpha position between the carbonyl and the newly formed alcohol or hydroxyl group. I'm going to form another enolate by drawing a second hydroxide and doing a deprotonation. Remember, be careful. It's tempting because it's faster to draw. This is an E2 reaction and a concerted process, but that is not what is shown to be the likely mechanism of this reaction. So instead of drawing E2, we're going to just go ahead and form the conjugate base. Again, I can deliver these electrons to this carbon, right? Or I can move the electrons all the way up to the oxygen. So if I want, I can go all the way up to the oxygen. Forming an enolate, which then kicks out hydroxide. And we formed the product in that step. Hydroxide in that last step. So again, this process, right, is called an E1CB mechanism. So make sure to draw the elimination as a two-step process, right, where we form the conjugate base and then do the elimination from the conjugate